Thank you so much. So, good afternoon, everybody. My name is Edgar Virguez. I am a third-year PhD candidate at the Nicholas School of Environment. And today I'm going to give an overview of the research I developed since I started the Energy Data Analytic Fellowship, that it's titled Utility Scale Photovoltaics plus Storage, a cost-effective alternative for decarbonization. So I'm going to start by providing a brief overview of the motivation of the work, then I describe briefly the methods, and I'll present some of the findings and the conclusion of the research. So the objective of the research was to identify a cost level of deployment of storage to support utility-scale photovoltaics in a vertically integrated service region. What I mean with this is, when I mean utility-scale photovoltaics, I mean solar panels in which capacity is more than 1,000 watts, it's in the order of megawatts, and that are operated from a central operator. And when I refer to storage, I refer to what we call bulk storage, or in our specific case, we use lithium-ion batteries, but we are referring to this big magnitude scale that could provide reliability and bulk scale services to the grid. So the idea with this study was to understand for a specific decarbonization target, so for example, the state of North Carolina wants to reduce 20% the carbon emissions, how can they achieve this by using a system that is comprised by solar panels and storage. This study is based on the conclusion of several studies that conclude first, that these kind of systems composed by PV and storage are essential for decarbonization. If you see most, or at least all of the studies that I have researched about how to get to a decarbonized, meaning that we don't produce or we capture all the carbon emissions, both PV and storage are main components of that. And second, the value or the benefits that storage provide to the PV systems depend exclusively on how much should you want to decarbonize. If you want to reduce 50% emissions, the value is much different if you want to reduce 100% emissions. So in order to select a study area to analyze a specific region, we try to look at the different systems in the United States. After reviewing them, we choose the Duke Energy Carolinas and Duke Energy Progress Service region that service in both North Carolina and South Carolina, and it's operated by Duke Energy. And we choose this region because of three main reasons. First, both North Carolina and South Carolina have currently different policies that require both states to actually increase the participation of renewable resources. This means that the electricity that is generated in both states have to have a bigger participation of PV, of solar and wind resources in the next 5 or 10 years. Second, we have seen a large potential of continuing trend of photovoltaics installation. To give you an example, during the period of 2015 to 2018, the amount of installations in South Carolina grew 9,000%. So this is like a record in the United States. And actually North Carolina is ranked second as the state in which we have a big installation. So these states are really like key players in this aspect. And third, because of the way we generate electricity, we have what we call rather inflexible resources. We depend a lot of nuclear reactors that we cannot ramp a lot. When I say ramp, is change the amount of electricity that's being generated from one time to another. So we have problem to integrate what we call intermittent resources, like the electricity produced from PV panels. So what we have is this kind of this system. So we want to answer again the question of how storage could actually increase the effect of producing electricity from PV systems. To do this, we comprise and we construct an experimental design of 31 scenarios in which we explore 3 specific capacities of PV, 6 gigawatts corresponding to approximately 5% of the total electricity generated in the service region by PV panels, 15 gigawatts and 30 gigawatts. So what we did is, for each of these capacities, we simulate 10 levels of storage. So all these percentage refer to the fraction of capacity of PV panels. So for example, as I've shown here in the graph, we have the baseline and we don't have any PV or any storage, and then we have 10 scenarios for each of the capacities, and we actually have a specific value of the capacity of photovoltaics, and then we simulate different levels of storage supporting the system. That would allow us to understand, as we increase the amount of storage support in the PV system, what will be the result. How do we actually evaluate the result of the system? We use different data science processes and algorithms to create what we call the unit commitment and economic dispatch model. This simply is a model that represents the process in which electricity is generated, procured, and generated in the service region. So what we did is we use the 222, we use a expanded version of the representation using all the generators that we have in the region. We use an hourly resolution. We choose year 2016 to do all the analysis. And we use several data sources to represent this, that it's a computer model, that it's comprised of 6 different models that allow us to represent how electricity is generated, what would be the cost, what would be the environmental discharge, what would be the reliability of the system. Mainly we have 3 components. One is pre-processing, that we use different data science methods to understand and to estimate, parameterize each of the units. Then we do a specific optimization simulation to understand which units will provide and generate electricity at all the times. And then we do a post-processing to find the impacts over the system. What do we find in terms of carbon emissions? As you can see in the graph, in the y-axis you have the carbon emissions expressed in pounds, million pounds per year. In the x-axis you see the 31 scenarios. What we see is in the baseline, you'll see each of the bars are comprised by 3 colors. Green represents the amount, the carbon emissions generated when each of the units is generating half of the capacity, so it's what we call a low loading. The blue bar, it's the emission that is generated when it's operating more than 50% of the capacity, what we call high loading. And the purple are the emissions related to when the units are being starting up, so when we turn on and off the units. So first what we can see is, as we expect, as we deploy more utility scale PV and we support with more storage, we see a dramatic reduction in carbon emissions starting from almost 90 million pounds per year. That's sometimes a number that's difficult to understand. But for give you a reference, we have an emission factor of 530 pounds of CO2 per megawatt hour. In the United States, the electric system is around 800 or 900. So we're starting at really clean, and it's clean because we have a lot of hydroelectric and nuclear resources in this area, so it's pretty clean. But in the most aggressive scenario, in which we actually deploy 30 gigawatts and support it with a little bit more of 6 gigawatts, 30 gigawatts of storage, we decrease the carbon emissions by 67%, so we achieve a big reduction. Also, we found that most of the reduction is actually located in the green bar. If you see how all the different bars are actually being diminished, the green bar is the one that it's mostly affected. So this is important because for the first time in this kind of studies, we use what we call partial loading emission factors. So we give specific emission factors to each of the units depending on the type of loading that they were going to use. So we actually found that the cycling effect of going up and down is not as important as we thought before. So this was also relevant. But in order to understand not only the carbon emissions, but the effect over the system, the economic effect, we actually calculate what is the cost of abatement. This is just a metric representing how much money are you paying to prevent 1 ton or 1 unit of CO2 of being generated. As we have here in the y-axis, we have the cost of abatement of carbon, and we have here 30 of the scenarios. We ignore the first scenario because we are comparing to the baseline, so this is just a change over the scenarios. And we have the cost of abatement ranging from sometimes like 38 to a little bit more than 130. For you just to have a reference, the social cost of carbon, that it's a metric that it's can be discussed how the impacts of that, but it actually represents what would be the estimated benefits of reducing 1 ton of CO2. Using a 3% rate, the Environmental Protection Agency estimates that it's $42 per ton of CO2, and we see that even some scenarios have some cost of abatement that are below that, so that could be interesting. But in order to summarize our findings, let me introduce this graph. So right here we have also the cost of abatement in the y-axis, and here we have a metric describing the ratio of battery power rating to utility scale capacity, meaning 0 meaning that for every megawatt of PV we don't have storage, 1 meaning that for every megawatt of PV we have 1 megawatt of storage supporting that. And as we see the 3 capacities that we simulate, we have a non-linear result that was pretty interesting because this is the first time actually that one of the first times that this has been reported. And as we can see, exactly at 12.5%, we achieve lower, like the most cost-effective reduction. When we mean cost-effective is reducing the most amount of carbon emissions with the least amount of resources. But as you may understand, each of these points actually produce a different amount of carbon intensity. So depending on which is your decarbonization targets, you would choose a different option. So for example, if you want to achieve a 20% or 25% carbon intensity reduction with these kind of systems, even though this is cheaper, you would actually have to go all these places because you will reduce more carbon emissions. So what we also found is kind of the maximum amount of reductions that could be achieved with the different systems. So we understood that starting from 6 gigawatts, we obtained a 21% reduction, and with 30 gigawatts, you obtain a 67% reduction. So with this in mind, I'm going to present the conclusions of the study. First, we were able to show that in order to minimize the cost of abatement, the PV capacity that we installed must be backed with at least 12.5 of storage. We also found that more storage raises the cost of abatement, but at some point there are some trade-offs in which we actually have a point in which it's better to not install more storage but install more PV. So we are actually studying that in a second publication. Third, we actually found the different cost-effective configuration for the 3 different components, and we actually found the different both carbon intensity reduction and the different associated prices. With this in mind, I want to thank my advisors, my peers, and the sponsors for this work, and I want to thank you for being here. Thank you.